Sheila is investigating the number of grey square tiles needed to make patterns in a sequence. The first 3 patterns are shown below. This is the first pattern, this is the second pattern, this is the third pattern. And the sequence continues in the same way. In each pattern, the tiles form a square and its 2 diagonals. So we have a square and its 2 diagonals. We have a square and its 2 diagonals. We have a square and its 2 diagonals. There are no tiles in the white areas in the patterns. There are only grey tiles. So here we have question A, B, C, D, E and F relating to the question. So press pause and have a go at them, and then when you're ready for the solutions, press play. And as you can see, we're only given the first 3. So what we're going to have to do is draw out the next 2 patterns. So the first pattern, again, it's a square with diagonals. And if we count up all the grey boxes, we have 21 tiles. So it's 5 across and 5 down, and then we have the diagonals. So 21 tiles altogether. In the second pattern, we have 33 tiles. So it happens to be 1, 2, 3, 4, 5, 6, 7 across and 7 down, and the diagonals as well. In the third pattern, we end up having 45 tiles. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9 across, 9 down, and the diagonals too. So we had 5 across and 5 down, then 7 across and 7 down, and then 9 across and 9 down. So now we're going to have 11 across and 11 down, and then 13 across and 13 down for the fourth and fifth. So for the fourth we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 across and 11 down on the diagonals. And when you add them all together, we've got 57 tiles. And then for the fifth, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 across, 13 down, and then the diagonals. So another pattern you may have seen was that we started off with the 4 corners. So 1, 2, 3, 4 squares, and then we had the 4 corners on the top right, the 4 corners on the bottom right, and the 4 corners on the bottom left. And then there was a single square in between each of those. In the next pattern we had the 4 corners, and then we had 3 across, 3, 3 and 3. Then in the next one again we had our 4 corners, and then 5 across. So it just might be another way you might see the pattern, but the best way probably to see it would be just to count the top row, 5 and 5, then the top row, 7 and 7, then 9 and 9, 11, 11, 13, 13. So the sixth would be 15 across, 15 down, and the diagonals. The 7th would be 17 across, 17 down, and the diagonals, and so on. So we're going to take these numbers, 21, 33, 45, 57, 69, and we're going to put them into a table. So question A says, in the table below, write the number of tiles needed for each of the first 5 patterns. So in pattern 1 we have 21 tiles, pattern 2 33 tiles, pattern 3 45 tiles, pattern 4 57 tiles, pattern 5 69 tiles. Part B. Find, in terms of n, a formula that gives the number of tiles needed to make the nth pattern. So the nth pattern, or the nth term, is also known as Tn. So we write 21, 33, 45, 57, 69. So I've written that in green. We get the difference to get from 21 to 33, we add 12. To get from 33 to 45, we add 12. To get from 45 to 57, we add 12. To get from 57 to 69, we add 12. So we know we're going to have 12n in our answer. And this is an arithmetic sequence because the first difference is the same. Now, one way to get the nth term is to start at the first term and just go back by 12. So since we're going up by 12 each time, if we subtract 12 from 21, we get 9. So this we could call term 0, since this is actually term 1. So we have 12n plus 9. So that's like a shortcut method to actually get the nth term. But using the formula, we have Tn equals a plus n minus 1 times d, where a is the first term, which is 21, and d is the common difference, which is 12. So we swap the a for 21, then we have plus n minus 1, and then we swap the d for 12. So 21 is the first term, and d is the common difference of 12. And then we multiply out the brackets and simplify. So we get 21 plus 12n minus 12, because n multiplied by 12 is 12n, and minus 1 multiplied by 12 is minus 12. And then we simplify. So we have 12n, and then 21, take away 12 is 9. So we get 12n plus 9, which is what we had over here as well. Part C. Using your formula, or otherwise, find the number of tiles in the 10th pattern. So we're going to take the nth term that we worked out in part B, and we're going to swap that n for 10 with brackets around it. So get 12 multiplied by 10 is 120, plus 9 is 129. So in the 10th pattern, we will have 129 grey tiles. Part D. Sheila has 399 tiles. What's the biggest pattern in the sequence that she can make? So we're going to take the nth term, which we worked out to be 12n plus 9, and we're going to let it equal to 399, because we know she has 399, and then we solve for n. We get the n on its own. So we want to get rid of the single number first, which is the plus 9, so we minus 9 to both sides. Or you could say you carry the 9 over the equal sign and it becomes minus 9. So we have 399, take away 9 is 390. So we have 12n equals 390. We want to get the n on its own, so we divide by what's stuck in front of the n. So we divide by 12 and divide by 12. So we have n equals 390 divided by 12, which is 32.5. Now remember, n has to be a whole number. It has to be a positive whole number. It has to be a natural number, because we're looking for which sequence. So you can't say the 32.5 sequence or the 32.5th sequence will have 399 tiles. That doesn't make sense. So if n is equal to 32.5, then the biggest pattern is going to be the 32nd sequence. So if we were to draw out the 32nd pattern, or draw out all the patterns up as far as number 32, when we add up all the tiles, we would have enough in 399. So if we were to have a look at the 32nd sequence, the 32nd pattern, if we put 32 into our nth term, so swapping that n there for 32, we get 12 times 32 plus 9 is 393. So Sheila has 399 tiles, so for the 32nd pattern, she'd need to use 393. So she can do that. She does have enough tiles. She will have a few left over. She'll have 6 left over. But she won't be able to make the 33rd pattern, because 12 times 33 plus 9 is 405. So she needs 405 tiles for the 33rd pattern, and she only has 399. So she does not have enough to make the 33rd pattern, but she does have enough to make the 32nd pattern. Question E. Find in terms of n a formula for the total number of tiles in the first n patterns. So when we hear total number of tiles, we want to think add. So if we were to add all the tiles together, if we were to add them up and get a total amount. So when we're thinking about adding patterns or sequences, we want to think of the sum of series formula. So we had already filled in this table. So the first pattern has 21 tiles, the second pattern 33 tiles, the third pattern 45 tiles, the fourth pattern 57 tiles, and the fifth pattern 69 tiles. So we know that A, the first term, is 21, and D, the common difference, is 12. So we're going to use our sum of series formula, which is Sn equals n divided by 2 multiplied by 2a plus bracket n minus 1 times d. So we're going to swap the a for 21 because that's the first term, and the d for 12 because that's the difference. And we don't sub in anything for the n because we're looking for a formula in terms of n. That means we want n in the formula. So we want n in our answer. So we're not going to substitute anything in for n. So we have n over 2 multiplied by 2 times 21 plus n minus 1 times 12. So n divided by 2 is the same thing as a half n. So anything divided by 2 is really multiplied by a half. 2 times 21 is 42. N times 12 is 12n. And minus 1 times 12 is minus 12. Then we still have a half n. 42 minus 12 is 30. We bring down the plus 12n. And next we're going to multiply in the half. A half times 30 is 15, or a half of 30 is 15. And a half times 12 is 6, or half of 12 is 6, and we still stick on the n. So we still have the n in front, we didn't do anything with that. And we've n times 15 plus 6n. Now we can multiply in the n. N times 15 is 15n, and n times 6n is 6n squared. So here we have Sn, which is a formula for the total number of tiles in the first n patterns. So now let's say if we wanted the total number of tiles in the first 10 patterns, for example, we would swap each of these n's for 10 with brackets around it and multiply it out. So total is where we add all the tiles together. F. Sheila starts at the beginning of the sequence and makes as many of the patterns as she can. She does not break up the earlier patterns to make new ones. For example, after making the first two patterns, she has used up 54 tiles because the first pattern had 21 tiles and the second one had 33, and 21 plus 33 is 54. How many patterns can she make in total with her 399 tiles? So we worked out this Sn formula from the previous question. So we said Sn is equal to 15 plus 6n squared. So we're going to swap Sn for 399 and we're going to solve for n. So we have 399 equals 15n plus 6n squared. So we're going to bring everything over the left hand side of the equal sign. So we'll bring down the 6n squared, we'll bring down the 15n, and then the 399 goes over the equal sign and becomes minus 399. And we let this equal to 0. So we've 6n squared plus 15n minus 399 is equal to 0. So here we have a quadratic trinomial. So it's quadratic because it has an n squared, and it's trinomial because there's 3 parts. We have an n squared, an n, and a constant. Now we can simplify this more by dividing across by 3. 6n squared divided by 3 is 2n squared, because 6 divided by 3 is 2. 15n divided by 3 is 5n, because 15 divided by 3 is 5. And minus 399 divided by 3 is minus 133. So we have 2n squared plus 5n minus 133 is equal to 0. And now we want to solve for n. So we label our first term, our n squared, our 2n squared as a. We label our second term, which is 5n, as b. And we label our third term, which is minus 133, as c. But just be careful here because you're actually using the 2 for a. So we're going to forget about the n squared now. So a is going to be equal to 2. And likewise, b will be equal to 5. You'll forget about the n. And c is equal to minus 133. So we're going to use our minus b formula, or our quadratic formula, which is in our formula books. And this is what we use to solve a quadratic trinomial. So the formula is x equals minus b plus minus the square root of b squared minus 4ac, all divided by 2a. So we have the minus, we bring down the minus. It's very, very important not to forget the minus, easily done. We swap the b for 5 with brackets around it. We do not swap it for 5n. Then we bring down the plus minus, and then we have the square root. And then the b squared becomes bracket 5 bracket squared. Very, very, very important to use brackets here, because if this had happened to be a minus, then you would have ended up with a minus answer, and that's not what you want. So we have bracket 5 bracket squared, because remember the b is equal to 5. You do not have an n in here. Then we bring down the minus, and then we bring down the 4. And then the a, we swap for 2. So we have 2 with brackets around it. And then the c, we swap for minus 133. Again, you must use brackets. And then that's all divided by 2 times a, which is 2 times 2, because a is 2. And we have brackets again. So at this point, you should have no n's. It should just be numbers. So minus times 5 is minus 5. You bring down the plus minus. And then you have your square root, and everything that's under the square root can go into the calculator all in one go. So you would not put the square root in necessarily. It's no harm just to do the square root in another step. So we have 5 squared minus 4 times 2 times minus 133 gives us 1089. And that's all divided by 2 times 2, so divided by 4. Okay, so we're going to break this up into 2 parts now, one with a plus and one with a minus. So we have minus 5 plus the square root of 1089 divided by 4. So minus 5 plus the square root of 1089 divided by 4. Or we're going to do the same with the minus. Minus 5 minus the square root of 1089 divided by 4. So minus 5 minus the square root of 1089 divided by 4. So basically we just broke this apart into 2 sums, one with a plus and one with a minus. So you can put this all into the calculator in one go. I'd use the fraction button, and my numerator would be minus 5 plus the square root of 1089, and my denominator would be 4. And you'll get 7. And then likewise do the same with this, and you get minus 9.5. So we wanted to solve this quadratic, and we solved, and we got 2 answers for n. We got 2 solutions, 7 or minus 9.5. But remember, we're looking for how many patterns she can make in total with her 399 tiles. So it does make sense to say that she could make 7 patterns, but it does not make sense to say she could make minus 9.5 patterns. That does not make sense. So the answer must be positive, so 7 patterns can be made with 399 tiles.